carriera cinematografica.
Sì, il nuovo
His book recently came out last year. Called String Theory and Scientific Computation and Scientific Method. String Theory and Scientific Method. And he's going to talk about some issues that are coming up about modelling scientific confirmation.
Yeah, what I will do is I will present a model of scientific confirmation that reaches out a little bit beyond what one would usually understand scientific confirmation to be. I will be very brief on the motivation for the problem, which is from fundamental physics, and then focus on the main general ideas of the way one can formalize such a problem. So the background is that in fundamental physics today, there are increasing time lags between theory building and empirical confirmation. And that's a serious problem for the field. It leads to a situation where it is very important to make up your mind about a theory, even in the absence of empirical confirmation. And what is interesting about it is that in some cases, with respect to some theories, physicists have rather strong opinions about the validity of that theory. String theory would be one example, cosmic inflation to a certain extent another example. And so there has been quite an intense debate on the question whether those quite strong opinions about a theory's viability are justified. Basically, there are two ways to deal with that. One way is to understand what's going on there, mainly in terms of a sociological phenomenon, or in terms of, let's say, a desperate situation in the absence of empirical confirmation. And the other option is to look into those kinds of reasonings which play a role there, and ask the question whether those kinds of reasoning are actually scientifically legitimate, and whether therefore they should be taken seriously. So the main question first is, do those assessments which lead up to such strong trust in empirically unconfirmed theories, do they have epistemic value? And a more far-reaching question is, can they actually be modeled as theory confirmation? So of course, that second step is not the only way to attribute epistemic value to such assessments. The reasons why I want to move in that direction will become clearer later on. So, what is theory confirmation as we know it is based on the prediction a theory makes. So a theory predicts certain empirical outcomes of measurements, and if that predicted data is found, then this confirms the theory. If there is no measurement of data that is predicted by the theory, there is no confirmation. The idea now is that it might, or the question first is whether it may make sense to widen that concept and include observations which are not predicted by the theory into that confirmational scheme. So you may say that observations which are not predicted by the theory still, in a sense, confirm that theory. The question is, does this make sense? And in order to answer that question, first, of course, we have to clarify what we mean by confirmation. So what is for sure necessary in order for that approach to make sense is that confirmation must be based on some observations. And that condition is by definition fulfilled in our approach, because we are talking about observations which are just outside or beyond the intended domain of our theory. The reason why such observations were not considered in terms of theory confirmation have a lot to do with one aim of limiting science from non-science by creating a scheme of the scientific process. So first, obviously, the hypothetical deductivism is based on the idea that we just look at confirmation within the intended domain, and on that basis, for example, logical empiricism, which was highly influential in the early parts of the 20th century, focuses on empirical confirmation because they want to build their entire concept of meaning based on empirical confirmation. So there is no motivation or no leeway for extending the concept of confirmation in that context. And a second position that still is actually very influential in science and also in physics today is the Popperian view, where you have this concept of falsification, and falsification obviously also necessarily has to proceed based on empirical testing. So the question is whether there is empirical confirmation or refutation. So there is no role for data beyond the intended domain from that perspective either. If we look at more recent perspectives, there is, one may say, less interest in the delimitation between science and non-science. There seems to be a stronger focus on the question how we can model the scientific process in general. So for that reason, there is more flexibility in modeling science and also in modeling confirmation. One very popular approach for theory confirmation nowadays is Bayesianism, which relates confirmation to truth on a probabilistic basis. So the idea is that we have a hypothesis H, and we can make the statement T that the hypothesis H is true, and then based on the base formula, we try to understand whether or not the probability for T given E is higher than the probability of T, and if that is the case, then we say the empirical data E confirms the hypothesis H. Now, generally, or let's say canonically, Bayesianism still adopts the focus on data in the theory's intended domain. So data that is predictable by theory H. And one reason for that is that arguing in favor of confirmation in that case, of course, is most straightforward. Roughly speaking, the idea is that if we look at a certain empirical prediction of a theory, and it turns out that that prediction is vindicated, there may be other theories which predict other outcomes, and those theories are ruled out, and therefore we can increase the probability of those theories which actually predict the given outcomes. And that's the rough idea why there is obviously prediction confirmation based going on based on successful predictions in the intended domain. So the question is, does this mean that Bayesian confirmation is naturally constrained to empirical data in the intended domain? And the answer is no, it is not. One can model confirmation by observations beyond the intended domain within a Bayesian framework. And what I want to call this kind of confirmation non-empirical theory confirmation, NEC in short. So before presenting this model, we have to make one step backwards, kind of. That is, we should better avoid the concept of truth in this analysis. Canonically, Bayesianism is formulated in terms of truth probability, but there are various reasons for avoiding that in this particular enterprise we are interested in. first, there is the general reason that physicists often don't ask for truth, but they rather want to develop theories which are predictably successful. So that's what they are actually interested in. And even more seriously, often we know that our theories are not true. They may be inconsistent, we know that they have certain limits of applicability and so on. Another reason is that Bayesianism normally focuses on probability increase. It is often left fairly unclear what the situation would look like in terms of absolute probabilities. So the question of absolute probabilities kind of plays a role in Bayesian analysis, but it's not emphasized. Actually, often it's more or less under the carpet, one might say. As it turned out, in our approach, it will be important to have absolute probabilities. So, since absolute probabilities in terms of truth are strongly dependent on your philosophical position with respect to truth, general assessment of the situation, if we want to talk about absolute probabilities, it's not a good idea to talk about truth. Therefore, we want to introduce a concept that is weaker than the truth concept, and that in a reasonable way represents what scientists are actually talking about when they trust a theory. So what they are actually talking about when they trust a theory is they talk about trust in the predictions of that theory within a certain regime. So what we are going to do, we will talk about viability, a theory's viability, which means the fact that the theory's prediction in its core regime, in some defined regime, are correct. So this is kind of a local approach towards the status of a theory. It doesn't reach all the way to truth or to absolute empirical adequacy. And it is directly related to prediction, which we want it to be. So that's going to be our focus. Now, what is the basic idea of non-empirical theory confirmation? In our case, we have the statement T denoting the hypothesis H is viable, which is the wrong letter, but in order to be traditional, I want to keep that letter. And we want to introduce an observation F, rather than E, that does not, that is not predicted, that's not correct, I wrote it here, that is not predicted by the theory H. It's not within the intended domain, that it cannot neither be predicted nor excluded by the theory. However, there is another hypothesis Y which does predict the observation F. And the viability of that hypothesis Y is correlated with the viability of H. So if we assume conditional independence between H and F given Y, we have this schema I wrote down here. We start with a probability increase of Y given F compared to probability of Y, and we have a probability increase of T given Y with respect to T. And so I don't know why I did something strange here, that should be an arrow. So we end up having confirmation in a Bayesian sense. Now, if we compare the situation here with empirical confirmation, we look at the Bayesian network of the cases. We first have empirical confirmation where we have this very simple relation, and in the case of non-empirical confirmation, we have no direct connection between F and T, no kind of direct implication there. But we have probably increase given y for t as well as for the non-empirical evidence f. Now the question, of course, is, so this just gives the general framework and explains in general terms why non-empirical theory confirmation can make sense at all. The question is, what can we use as non-empirical evidence, and what can we use as a hypothesis of that kind that provides the structure we want to have. And two general requirements we want to fulfill is, first, that the implication of non-empirical evidence for that hypothesis y may be subtle in some way, but it should be a rather plausible and clear connection. And the second requirement is that the core concepts which are used with respect to non-empirical evidence and also with respect to the statement should not be overly vague. So more specifically, we want to avoid concepts like beauty, simplicity, elegance, or all that kind of things where we don't really know how to attribute any value to those parameters. So on that basis, what we want to do next is we want to check how physicists actually argue. And if we look at the kind of reasoning that's going on there, one very prominent argument is what I want to call the no alternatives argument. So the idea is that scientists have found one theory that either fits the available data, that's the ideal case, or it makes the promise to fit the available data in some cases. But the theory's core predictions have not been tested. And now, despite considerable efforts, no alternatives have been found to this particular theory. And from that fact, it is inferred that the theory is probably viable. So maybe the best recent example for that kind of reasoning is the attitude towards the Higgs particle before the actual discovery of the Higgs particle in 2012. So why do physicists relate the lack of alternatives to viability? Of course, that's a highly non-trivial step. There may be different reasons why they haven't come up with an alternative theory. So first, what is important here is that physicists must share a certain scientific optimism, meaning they must be convinced that there actually is a viable theory, otherwise the argument wouldn't go through at all. And then they must have the understanding, just in order to have any non-empirical confirmation there at all, they must have the understanding that the less possible alternatives there are, the higher are the chances that scientists picked the viable one. So in the extreme cases, that's quite obviously true. If I just have one theory, one possible theory, and if I find a theory, I will have found the only possible one, and if there is a viable theory, that's going to be the viable theory. If I have a huge number of theories, and I pick one of those out of that huge number, the extreme case would be I have a free parameter, and I just pick one value, I won't have any expectation that value will be correct. So it's clear that there is some correspondence there. So computer transformed all my arrows into that one.
No, so that stands for an arrow. Now we know an arrow.
Okay, now it's an arrow, yeah. So this means that, so on that basis, if scientists make that assumptions, they make a step from observing something with respect to their their, let's say, to their subjective perspective, meaning that their perspective only includes one theory they know of, to an absolute statement kind of about the world, about the actual spectrum of possible theories. And they claim that if we have only found one theory, actually it's probable that there actually are just few theories. And so this statement that there are actually few theories then constitutes a natural candidate for that hypothesis. Why? If we can infer why from the observation that we haven't found any alternative theory, and if, as we have said, y implies a high probability for the viability of the hypothesis H, then we have empirical confirmation. Now, of course, a number of questions must be addressed in order to clarify what's going on here, and I have no time to go into those questions, but still I want to mention them because they're important. First, the question is, what is the framework within which this argument is being carried out? So the framework is that we only want to admit scientific theories, so we meet some scientificality conditions. The question is, what are those scientificality conditions? And the second question is, how do we kind of count theories? So how do we carry out theory individuation in this case? Just one remark about theory individuation. The question of theory individuation is strongly depends on the question what we expect from the theory. So if we have a certain expectation with respect to the prediction of a specific theory, theory individuation has to be designed in order to be a meaningful foundation for that predictive claim. So once again, going back to the case of a free parameter, we might ask the question whether a theory if we have a free parameter in a theory, we might count each value of that parameter as an individual theory. This does not make sense in this context for the simple reason that no one takes seriously individual values of free parameters as a prediction. Therefore, we don't claim predictions based on choosing arbitrary values of free parameters. Therefore, theory individuation should not proceed along that line. So that's just a very rough idea. So if one looks more closely, formally into that scheme, it turns out that you can formalize that, and you can actually show that based on a set of assumptions, you get empirical confirmation here. So that's a paper in cooperation with Stefano Hartmann and Jan Spranger. So what we do here is we introduce a set of available data, a set of constraints, what I call scientificality conditions. Then we have the hypothesis that explains the data D and satisfies those conditions. And we have empirical, let's say, a set of future experiments that in the end will decide the viability of theory H. And then we introduce the propositional variables T and non-T, meaning that H is empirically viable or it's not, and an infinite value Y, where this index I counts the possible alternative theories. And then we have the statement about the non-empirical evidence. Scientists have found no alternatives to H, or scientists have found at least one alternative. And on that basis, what we need further is a set of assumptions. So it's not the case that Bayesianism automatically leads towards stating confirmation in this case, but those assumptions are actually fairly mild. They are significant, but they are fairly mild. First, you need the assumption of conditional independence, which I already mentioned, and then we need let's say the weakest possible correlation between f and y and t and y along the lines I presented it earlier on. So as long as once one has that, one can show that there is non-empirical confirmation going on in this case. Now, just showing that there is no non-empirical confirmation does not mean that this kind of confirmation is actually that it's a good idea to trust this kind of confirmation. It may be just minimal confirmation, and we, in order to understand whether we want to trust it or not, we should have a way of gauging that kind of confirmation. And there is an obvious problem within the context of an alternative argument, and that problem is that there is not just one possible reason for this non-empirical evidence, for the fact that scientists have found alternatives. There may be that there are no alternatives. The alternative is that scientists are just not diligent, not capable enough for finding those alternatives. So this means that if scientists would just rely on alternatives arguments, they wouldn't get very far. One might also say that an alternatives argument on its own may be applicable in many non-scientific contexts as well, and usually won't be a very good argument in those contexts. So, yeah, basically, that's what I just said. One may even strengthen that problem, emphasize the problem a little further by saying that usually one may even expect that A will be the stronger argument, the stronger reason for a lack of forthcoming alternatives than Y. So what we need is another argument that is capable of splitting between A and Y. And an argument that can do that job is what I want to call the meta-inductive argument. And this argument is also quite widespread in fundamental physics, and plays a very important role. And it is based on looking at other contexts of predictive theories that have not been empirically confirmed, and asking the question whether those theories tended to be empirically successful. Now, of course, it's not the case that any model or any theory that has been developed has been or will be empirically successful. So one needs to introduce certain conditions, which I call B here, which define a context within which we can expect empirical success of the theory. So one element that enters in those conditions is what we already know from the alternatives argument. We need situations where we actually just have one theory. If we have situations with 1,000 theories, no one can expect a single of those theories to be empirically viable. And there may be other conditions. For example, one may have the condition that the specific theory provides a solution to a consistency problem. Let's say in high energy physics, I would probably introduce that assumption. So if I look at a research context, at a research program, and I notice that whenever such a situation arises, eventual empirical testing turns out to vindicate that theory, then it is concluded that a new theory that also fulfills the conditions will probably be empirically viable as well. So in this case, we once again have a similar structure. We have a structure where the non-empirical evidence now is the observation that other theories in the research field which satisfy certain conditions tend to end up being empirically successful. And the important point with respect to relating this argument to the alternatives argument is that in this case, the lack of capability on the scientist side is not an explanation for the non-empirical evidence. It's not an explanation for predictive success of a theory that scientists are incapable of finding theories. Therefore, what happens here, first what happens here is that we get an absolute ratio of empirical success, which kind of gauges the entire argument. And second, it provides a basis for the priors which I can introduce, the prior probabilities which I can introduce in the alternatives argument. So it kind of provides a reasonable point of departure for the alternatives arguments. If I have a very strong meta-inductive argument, on that basis strong no alternatives arguments, meaning that people look for a very long time and they don't find theories, carry more weight. So that means that what we see here is that those arguments are not independent from each other. On the one hand, I need the meta-inductive argument in order to support an alternatives argument. On the other hand, I need at least, let's say, a small, a modest version of an alternatives argument in order to have meaningful conditions for the meta-inductive argument. So there is a certain interconnection there. Then one should mention a third argument, the argument of unexpected explanatory interconnections, which is not as crucial for the entire conception of non-empirical theory confirmation, because it's not always there. It's not necessary to get the entire structure of the argument going, but in some cases actually unexpected explanatory connection play the main role in the eyes of physicists. For example, if you talk to string physicists about what is the main reason for their trust in the theory, they would usually first pick the unexpected explanatory interconnection. So once again, just very briefly, the structure, interestingly, is the same. That once again you can develop the argument based on the concept of the number of alternatives. I don't want to go into details here because I don't have time. I think when did I start actually? Okay, so I have 10 minutes. Yeah. So I can say a little bit about this actually. So the idea is that that we develop a theory based in order to achieve a certain goal. There is a close equivalent to the unexpected explanatory interconnections argument on an empirical basis, which is the novel confirmation argument. So in the case of the novel confirmation argument, what you argue is, what you do is, you look at a theory based on empirical data you already know, and then you check whether novel confirmations that did not enter the construction of a theory, actually confirm the theory. And there is a debate going on about whether a novel confirmation carries additional confirmation value compared to old evidence. But there are many scientists and also many philosophers of science argue that it actually does. Now, if you just switch from the empirical evidence context to the non-empirical evidence context, what you look at is the conceptual reasons for developing a theory. So you may have some consistency problem and you develop a theory in order to solve that specific consistency problem. And then you find out that actually the theory has implications which reach far beyond that problem you intended to solve, and for example provides interconnections between different problems, different aspects of a research field. So you get a far more coherent overall perspective on the physical situation. So if that is not the case, if a theory doesn't do anything of that kind, physicists tend not to have an awful lot of trust in the theory. There may be cases where meta-inductive argument plus alternatives argument on its own is strong enough to nevertheless to have trust. But often, if you don't find any unexpected explanatory interconnections, that's a very bad sign for a theory. While on the other hand, if you find lots of that kind, phenomena of that kind, it instills trust in the theory. And the interesting thing is that once again, one can understand that in terms of the question of the number of alternatives. Very briefly, the idea is that if we look at let's say the number of conceptual problems which are covered by an individual theory on a statistical basis, and we compare, once again, just to get the picture, the extreme cases, we compare a situation where there are lots of consistency problems, lots of conceptual problems, and there is just one theory, one possible theory that is able to solve one individual problem of all that spectrum of problems. We can, given that we are scientific optimists, we can be quite sure that actually that theory is going to solve all those other problems as well, because there is just one theory. So if we find one, we have it. While if we have lots of possible theories which are capable of solving that individual problem, we have no very strong reasons to assume that that solution will carry over to all those other problems. So if we find lots of unexpected explanatory interconnections, that can be understood as an indication of limitations to underdetermination, as an indication for a limited number of alternative theories. While if we don't have that indication. So we have no basis for trusting the theory. So on that basis, this argument of unexpected explanatory interconnections can also be formalized, probably, it hasn't been done that, but there are reasons to assume that it can also be formalized in this way. Now, what is the role of non-empirical theory confirmation compared to empirical confirmation? Non-empirical confirmation is an extension of the concept of confirmation. The non-empirical part is strictly secondary to empirical confirmations, however, and that's very important to emphasize. And the reason is that the meta-inductive argument is crucial for gauging the significance of non-empirical confirmation, and the meta-inductive argument relies on empirical confirmation in the research field, someplace else in the research field. So as long as we don't have empirical confirmation, we don't have non-empirical confirmation as well. And if we don't have any empirical confirmation anywhere for a very long time, non-empirical confirmation will suffer from that also. Of course, it is also important to emphasize that the concept only makes sense as long as one is ready to acknowledge that it makes sense to attribute probabilities, even though subjective probabilities, to the viability of a theory. In effect, most physicists do so, in a way. So if physicists are very highly convinced about the viability of the theory, they're ready to bet on that theory. So that's kind of expressing attributing probabilities in the decision theoretic sense. And second, it is also important to assume that high probabilities too make sense in some cases, because unlike the conventional Bayesian case of empirical confirmation, where first, let's say, the scientific relevance of empirical data is taken for granted, and second, there are those convergence arguments which support the idea that actually is coming from lots wide spectrum of subjective prior probabilities. We end up with something like more or less a consensus about posterior probabilities. In the case of non-empirical theory confirmation, we have to rely on absolute probabilities, which we get from the meta-inductive argument. So we need high probabilities in order to get strong non-empirical confirmation. And that also was, as I mentioned in the beginning, was the reason why we don't want to talk about truth here, just about viability. Now, if one accepts those assumptions, on the other hand, it seems highly implausible actually to reject non-empirical theory confirmation. What one should also note, of course, is that that non-empirical theory confirmation in this world never will provide the confidence in a theory that is provided by conclusive empirical testing. So conclusive empirical testing can generate probabilities very close to 1 with respect to a certain regime. Non-empirical theory confirmation will never get there because the argument is quite vague in many respects. So we can never be really sure about the theory's viability. But as one can see with respect to the Higgs hypothesis, actually the trust in the theory can be quite high in individual cases. Now, so far we have just talked about theories without any empirical confirmation. At the end, what I want to just sketch very briefly is that non-empirical theory confirmation plays a much more general role, actually, than just addressing situations where there is no empirical evidence, because often non-empirical confirmation works in conjunction with empirical confirmation, and often in canonical understandings of the scientific process, the role of non-empirical confirmation is kind of it's tacitly included within the concept of empirical confirmation once scientists have made up their mind with respect to interpreting the data. So, for example, if we look at cosmological data in the last 20 years, there was a supernova measurement which was an indication for cosmological constant. I wrote cosmic inflation, that should be cosmological constant. And now there is the BICEP2 data that may be an indicator of inflation. In both cases, it took many years to understand whether that's actually empirical evidence for the hypothesis in question. And the way of reasoning that leads up to that conviction at the end contains elements of non-empirical theory confirmation. It contains elements of understanding whether all alternative interpretations have been ruled out, and all those elements, all those kinds of reasoning which I presented before do play a very important role there. So it's not the case that we have either empirical confirmation or non-empirical one, but rather we have a situation where non-empirical confirmation always was part of the confirmation process. However, now we are in a situation where in some cases non-empirical confirmation kind of stands on its own and can be rather strong in the absence of empirical confirmation. So the conclusion, I would argue, is that non-empirical confirmation actually is an integral element of confirmation across the board. It hasn't been considered for for contingent reasons which have a lot to do with the development of philosophy of science throughout the 20th century. But in today's situation, we face a research context in fundamental physics where it's actually quite difficult to deny that non-empirical theoretical information does play a role. Thank you.
Questions? Yeah, you know.
So regarding this last point, it seems to be a different thing to say that NEC is an integral part of confirmation or offers a more realistic model of actual confirmation. That, you know, as physicists think they confirm theories. That's different from saying that it somehow captures how confirmation as a rational endeavor works. So even if you are right in saying that there are periods in the history of science where NEC is involved in this sort of way, one might disagree with the idea that confirmation ought to be understood in that way, that NEC ought to be viewed as being an integral part of what confirmation really is.
Yeah. But what I want to say is a little stronger than just saying scientists thought that way. So I do not just want to focus, as one might put it, on the context of discovery. So of course that was always acknowledged. It was always acknowledged that, for example, that there are those classical examples that Einstein believed in his theory just because he thought it's so beautiful that it cannot be wrong. Arguments of that kind. So in a way, if you think about it, you can phrase that in terms of non-empirical confirmation, what the argument he provides here. So no one would have denied that was going on. As you very correctly say, it's a different thing to say that actually it is a necessary element in empirical confirmation. And I want to make the latter claim. I want to say, in many cases, not always probably, and the role of non-empirical confirmation will be very different in some cases than in some contexts than in others. But there are contexts where it is very difficult actually to understand what's going on without introducing kinds of reasoning which are actually equal to those kinds of reasoning which enter in non-empirical theory confirmation. So these latest cosmological kind of discoveries or cosmological observations are very good examples. But there are other more historical examples which I think are very interesting as well. One I think very interesting example is the shift in the understanding of whether we can confirm or discover microphysical objects. Whether in the 19th century there was the general understanding that we actually cannot confirm atoms. It may be an awfully productive and progressive research program to introduce atoms, and many people would argue in that direction, while others wouldn't. But both opponents and supporters of the atomic hypothesis in the second half of the 19th century were basically in agreement, with very few exceptions, were in agreement that there is no way to confirm atoms because we cannot see them. So there always may be another theory that explains the situation equally well. It does not rely on the positive atoms. And one thing, for example, there is a very interesting paper by Maxwell, which was discussed by Peter Ackenstein in much detail, where Maxwell tries to, who was of course supportive of the atomist hypothesis, and he tried to introduce an intermediate epistemic quality to deal with the concept of atoms. So he said we have this problem. We have, on the one hand, unconfirmed speculations, and on the other hand, we have confirmable scientific hypotheses. And then we have something like atomism, where we know it's very useful. We know it makes a lot of sense to assume that. So we want to attribute some epistemic status to them that is different from speculation. But we don't have any. So he wants to introduce an intermediate concept there. So that was the situation in the 19th century, while in around 1910, when actually the idea was established that we can know that there are atoms, what happened there was that lots of kinds of reasoning which are quite similar to what is going on in non-empirical theory confirmation was kind of included in the concept of observation, of discovery.
Can I just very quickly, so accepting that in the history of science NEC has played a role, accepting that, I just don't see the arguments for saying that it's rational, it has been rational to do so.
It has been rational to do so in the sense that it allows quite reliable assessments with respect to the predictive quality of a theory. So, for example, if we assume atoms, if we discover a new particle, and we have this particle concept, it's not a classical particle concept, obviously, so it's not by no means a trivial question what it means to discover a particle. But still, discovering the particle will usually have lots of implications which go beyond the specific experiment where we discovered it. And we believe in those implications on that basis. And it turns out that more often than not, or very often actually, we are right in believing those implications. So in this sense, it is rational.
So there's some sort of meta-induction going on.
It proves itself in the research process.
No, but why would you describe the atomism case as non-empirical? I mean, the standard thing that, maybe it's really naive, but the standard thing I thought is, there's 15 independent different ways of measuring Avogadro's number, and they all gave the same number, so we believe in atoms on that basis. And this is pairing, and this is what leads to Frank Ray, who was previously a staunch critic of atomism. That sounds empirical to me.
I'm not saying that the discovery of atom is non-empirical, is based on non-empirical theory confirmation per se. What I say is that there is an element of non-empirical theory confirmation. Or you might also, if you might say there is an element of non-empirical theory assessment there that contributes to what nowadays is understood as empirical confirmation. And what I say with respect to this historic shift is that let's say the more pure understanding of what empirical confirmation amounts to, that was applied before 1910, did not acknowledge the possibility to confirm atoms. So you needed something else in order to make that step towards a situation where you did.
Sure.
What I say is that this...
But changing what counts as empirical confirmation isn't the same thing as accepting non-empirical confirmation.
Yeah, what I say is just saying that there was more empirical evidence is not the full story. Because before that, the idea was not that we just have not, that the empirical evidence is not in yet. But the situation before in the 19th century was that actually our concept of confirmation doesn't reach towards unobservable objects.
Okay, so I want to carry on, but I think we should get your question.
But I'll try to be as short as possible because people here are tired and so. Well, in the end, physicists are human beings, and so they are much less rational than you might think or believe. So one thing is what they say, and one thing is what they intimately feel about their theories. So it's a matter of fact that we theorists keep on producing theories even if they are very or hardly or possibly unrelated to empirical facts. Of course, we pretend that in the end there will be some empirical confirmation on our theory.
Yeah.
But mostly we say that they are case studies, and we are very happy whenever we learn things from a theory. Even if, for instance, we have to solve a technical problem to make a calculation, that itself is worthwhile, because you have learned something from the theory itself, even if the theory will be one day or another forgotten because or something. So we keep producing more theory than needed. And that's a fact. And in the end, I might say, for instance, that myself I dislike, this is just a matter of taste, I dislike string theory. But even if I had the possibility the power to do so, I would never force my colleagues to stop pursuing string theory, because of course they learn a lot of things from it, even if in my opinion, string theory is not a good theory that will explain something in the future. This is just a feeling, irrational, completely irrational feeling. Okay, and the second point is that physicists use those arguments like beauty, simplicity, elegance more often than it may be thought. You know, we like our equations. It's like a painter likes his painting, even if nobody will buy it. You know, it's a painting, you like it, you love it. It's your own painting. Nobody will buy it, but you love it.
Yeah, let me say, make two remarks.
Yes.
The first point is that claiming that they are related, actually, those remarks. Claiming that there is a rational core in this kind of reasoning does not imply that everything that is said in that context is actually rational. And so this is an attempt to isolate aspects which can be rationalized, and concepts like beauty, for example, are left out of that restructuralization for the very reason that I wouldn't even want to think about how to rationalize beauty. That's the first remark. The second remark is that arguing for a rational core of this kind of reasoning does not imply that anyone who uses these methods of reasoning it must be correct or must use it in a viable way, or people might exaggerate those kinds of arguments. Those arguments are more vague than other kinds of reasonings, quite obviously. So to say it pointedly, this doesn't prove the truth of string theory's claim that they believe that their theory is true or is right. So it is not the case that this denies the idea that there probably is, or there always is a sociological aspect in science, and that sociological aspect is particularly difficult to isolate from the rationalist core in cases like that. And that is, previously I just gave the argument why these non-empirical theory transformation has not been considered in philosophy of science for philosophical reasons. Of course, there is also that reason that it's not a very clean kind of reasoning, and it's very difficult to isolate sociological aspects from that rational core. So everyone who would acknowledge that there is non-empirical theory confirmation, and it makes sense to have trust in these kinds of arguments in principle, is free to argue that in some cases, in string theory, in cosmic inflation, with anthropic reasoning, whatever, that in that case, those arguments are not good arguments in those cases. They don't work in those cases or so on. So I don't want to say that this decides the case in favor of those using those arguments. What I want to say is that the debate should be based at the level where the viability of this kind of reasoning in principle is acknowledged, and the question is rather whether in those specific cases that's a good argument or not. There are cases where obviously it was a good argument. There are others where it's not.
That sounds a bit circular, because you started with this claim that physicists believe in string theory, and now philosophers have this challenge: do we say they're wrong, or do we change our view of theory or connection? But what you should more correctly say is there's a subculture of physicists that believe in string theory.
Sure.
And the vast majority of physicists, if you said to them, are there strings? They'd say, oh, that's not proven. If you said, is there dark matter? They'd say, that's not proven. If you asked a condensed matter physicist, or a person who works in optics, or someone who works in other areas of physics, they will say, I mean, I'm basing this on my experience of talking to physicists.
Yeah.
When we teach the foundations of physics to the physics students in the physics department, we tell them about what's the core of physics that everybody says is confirmed, and then we talk about where things are going. And string theory and dark matter are very much on the side of where things are going, as opposed to what's confirmed. Now, it may be that as a matter of psychological fact, there are many people who have faith in these theories, and they may be right. But you have to distinguish that from the institutional process by which things come to be accepted as scientific fact. And string theory has not passed that test, undoubtedly.
I think that calling it a subculture is
It is a subculture. I mean, the average physics department doesn't have anyone working on string theory.
Sure. But that is because they like it, and that's human. I mean, they will never write founding if they write in a project. I study strings because I like it. Of course. Come on. Nonetheless, if you ask them, they do that because they like it. Yeah.
So first, I mean, it's a subculture that involves about, I don't know, let's say 2,000 people, something like that. So it is a discipline, a scientific discipline.
I agree with
And
that.
the interesting thing is, so there are those who say that there is this sociological problem, this group thing within that group. On the other hand, there is an equally viable point made by that group itself, which is that they say, look, we are a quite considerable research field. We are as big as any other research field in theoretical physics, and we are the experts on that field, on that theory. And you're not. So why do usually what happens in science is that if there is a well-established and quite, let's say, considerable research field, and there is, let's say, not entire consensus, but there is a strong inclination towards a certain interpretation of the situation by those experts. People outside that circle of experts would tend to believe the experts, right?
Well,
they would
yes,
say, okay, they probably
they
have the best insight into that situation.
I disagree. I think most people would say we believe them when they tell us what the data is that supports their theory, and that's exactly why most physicists say, yeah, I haven't done the calculation for quantum electrodynamics, but I believe in quantum electrodynamics because they predict recover the magnetic moment of the electron to 13 significant figures, right? So, but nobody can say when they ask the string theorist, well, what did you do like that? Right? The string theorist doesn't have an answer. That's different to the Higgs boson. It's different to everything else in science that's accepted as scientific fact. And so that's the difference. I mean, yes, you don't just believe them on the basis that they're experts and they say this is what we think. You believe them on the basis they can claim to be scientists and not just theorists.
Right. But usually assessment of a scientific situation, not just in physics but in lots of fields, right, is based on lots of input on various levels. So, for example, if if you ask the question, should I believe, I don't know, the hypothesis that the extinction of dinosaurs was made by an effect of a measure. So there is no clear-cut physical proof of that, right? But there are lots of arguments, lots of kinds of reasoning. So you would assume, normally you would assume, that those people who spend their careers trying to investigate those questions have the best insight into that answer. So if they build a consensus in one or the other direction, you would say, okay.
But they're building a hypothesis to explain data.
So it would be a rather big step to say, well, I don't believe them,
but there
because
is no
from the
data
outside,
string theory is
I
to
believe,
explain.
I think that let me finish the sentence. From the outside, I believe that there is so much sociology going on in that field that they are, I don't know, they just are not to be trusted, even though they are the experts.
But they have a data set to explain. They have an empirical problem. Why did the dinosaurs go extinct? And then we say, oh well, like, yes, they're the experts. They agree this is the best hypothesis to explain that data, so we believe that. There is no corresponding data set in string theory. Also, of course, it's very misleading to call it string theory. There's no single thing.
There are many string
There
theories.
10 to 100 things.
Yes, there are many string theories.
That's 10 to 100.
Brain theories and whatever, proliferation.
String
But
minimum.
if you say to me, if I say what's the data, I mean at least with dark matter there is data to explain the acceleration curves of galaxies. But if you say what's the data that I need string theory to explain that I can't do with that, there's none. I have a standard model that explains all the empirical data at GR.
But the data tells you, the data you do have, which is data from cosmology, data from high energy physics, is that this data tells you that there are regimes where the individual theories you have don't suffice.
Right, but I have no data on those regimes.
Yes, I cannot test the theory. I have no empirical anomaly where I can say, okay, this measurement is at variance with the specific theory I have, and therefore I have string theory which explains that data. And that's right. But the point I try to make is that exactly this entire question, the question as to which kind of corroboration or confirmation of a theory is viable in a scientific context, in the end is up to the involved scientists.
Well, not if that involves changing our conception of science as a whole, because science
people
belongs
looking
to all
at
of us,
the
not just the
situation
string theorists.
from the outside acknowledge that. And in this case they don't, for the very reason that there is this shift going on. So there is this shift going on where the concept of empirical confirmation changes. Now, of course, you may say, okay, as a matter of principle, I don't accept that. I don't want that. And if anyone moves beyond my conception of what it means to have scientific confirmation, is not a scientist for me. But what I argue is that actually scientific confirmation is a more complex question. And it always was. Not just today in the presence of those theories and that strange situation, but it always was. It always was more complex than philosophy of science would let us believe. And similar kinds of reasoning, which already played an important role in those contexts with respect to empirical confirmation, are at play with respect to assessing.
I think this is slightly rhetorical, because you're suggesting that philosophers of science have this conception of confirmation, and it's our view. But if you ask any scientist in any field, they'll say science is about empirical confirmation, right? Any scientist, the first thing they say when they want to talk to another scientist is, what data have you got, right? How good's your data, right? This is not something that's been brought in from logical positivism or something. It's something fundamental to what we think of make the difference between science and other forms of inquiry. So I don't think we should think of it as, you know, my view of science or the philosophy of science view of science. It's much more just what everyone outside of string theory thinks science is.
Well,
First, sorry,
we should divide the string theories.
Yeah,
Yeah, so
there is, sorry.
sorry was it before, but I couldn't use my
it's just a
privilege.
small point, so maybe we'll have to. So I'm still not sure, so what supports the no alternative arguments? No alternative model or this NNA.
What supports the no alternative?
Yeah.
So what is the
So you need
non-empirical
that,
evidence?
you need that assumption, right? To build in that there's
Yeah.
no alternative.
So the no-empirical evidence is the observation that scientists have searched for alternatives to a specific theory and they haven't found it.
Okay, but they haven't found it yet.
Yeah, that's the
So-
observation.
String theories, there are many alternatives, many competitive string theories.
Yeah, so what, I mean, why should we expect that this will never achieve any alternative?
Exactly, that's exactly the question. So if you,
Are you assuming that that's not going to happen, or?
so what I say
This is
is,
your last word, Richard. We're going to stop when you've finished what you say.
We can
All right.
take it over the.
yeah, we can also, okay.
Please, no, have your last word.
Okay, so the
So there are no alternatives now.
yeah.
Then we
Yeah.
grant it
So,
that there is
okay.
probably.
The idea is that just to establish confirmation does not require assessing the significance of that confirmation. So there may still be a huge probability that eventually some alternatives will be found. However, there is the connection between no alternatives argument and meta-induction argument that allows to gauge the significance of no alternatives in certain research context. So if I were writing a case, for example, of the Higgs discovery in research context, where I know that in the past no alternative arguments have worked very well, I'm will be inclined to
Yeah.
The data is good.
We have to.
Andy, sorry, I didn't realize we were going to get cut off. But maybe we should come early tomorrow and carry on. Thanks very much.